buenas tardes, bienvenidos a la conferencia. Las personas que deseen registrar la asistencia están rotando una lista, por favor, para que se apunten y podamos llevar el control. Igualmente, a nombre del Doctorado en Ingeniería, darle las gracias al doctor Román Neruda, darle las gracias a ustedes por su asistencia. Vamos a comenzar con la presentación del doctor Román Neruda a cargo del profesor Juan Figueroa. Carlos Figueroa.
Buenas tardes, ¿se me escucha?
Sí.
Hoy vamos a tener una charla a cargo del profesor Román Neruda. Se llama Automated Machine Learning, How to Tailor Model to Data. El profesor Román Neruda estudió informática en la Universidad de Charles University, se conoce más como Carolina University. Hizo su doctorado en Computer Science en la Academia de Ciencias de la República Checa. Ha trabajado en diferentes proyectos con la Unión Europea, con Los Álamos, en el laboratorio de Los Álamos en Estados Unidos, bastante famoso. Ha trabajado con la Universidad Americana en Beirut. Ha dado diferentes conferencias por todo lado, incluyendo Colombia otra vez. Es autor de diferentes libros, diferentes artículos. Está dedicado más que todo a la investigación y al tema de Machine Learning, Auto Machine Learning y Meta Learning. Esos son los temas del trabajo. Es ya un buen amigo de la casa, es una persona que nos ha visitado varias veces y pues es un honor tenerlo acá. Dobrý den, profe. Pravda milujeme, že prací v auditě do naší země. Muchas gracias. Buenas tardes, everybody. Professors, dear students. It's a great pleasure for me to be here. So thank you very much, people from Doctorado program, especially Prof. Juan Pablo for taking care of me, and my parcero Juan Carlos. We know each other for a long time. I still don't speak Spanish, so I don't know what he actually told about me during. I hope it was nice. Okay, so thanks again, and let's start. My talk will be about machine learning and a special type of machine learning that tries to make it more automatic. So that's the idea. So how to make your model, machine learning model, better for the data, for particular data. That's the idea. I will try to present several ideas. I will not go deep. It's more like an overview of the topic. And I have actually tested this on a PhD student's summer school in Italy 2 months ago. It was a 4-hour tutorial. So I hope we all have 4 horas. It was a joke. It's not gonna. It's not gonna be 4 hours. It was a joke. Juan Carlos will tell me when I'm boring. I mean, after 1 hour, when I'm boring. 10 minutes. So don't worry. Also, this talk will have 4 parts, and after each of the 4 parts, you will see some calming image, like a tranquil image. So you know that the part is over, and the 4th part is really short. So I would also like you to, if you have any questions or comments, so you can prepare them, you can write them down, and in the end there will be questions and answers. I'd love to discuss these ideas with you. If you feel you don't understand something I'm saying, so just raise your hand and stop me, or if you don't agree with what I'm saying, well, yeah, we can discuss it. As well.
Si tienen alguna pregunta, no pueden pasar, yo les ayudo, no hay problema. Me dicen y
Yeah. I understand understand preguntas. There's several Spanish words I understand. Pregunta, café, dos cafés. I had 4 cafés before the talk, so I want to be away. Cerveza. I hope I will have some after the talk. Okay, so let's start then. The general field of artificial intelligence, we all understand what it is, although sometimes it's hard to define, right? Because, well, the ultimate goal of artificial intelligence is to create an artificial mind that's probably similar in capacity to a human mind, right? But we see this in science fiction movies and read it in science fiction novels yet, right? But on this way to this El Dorado, right, we actually have good successes in solving special tasks. So we don't have a general intelligence that's on par with humans, but we have specialized programs that can solve problems better than humans in special areas, right? And actually we now live in exciting times because the artificial intelligence is finally getting to real life. And one of the areas that is big now is machine learning, where it's part of the artificial intelligence where we actually use data to train the model, right? And then we use the model as the artificial intelligence systems. And there are many examples. You have smartphones in your pockets, so maybe you have applications for translation. That's what I use when I want to order food here. And it's deep learning. You know, the Google Translate, it's a model of deep neural network trained to translate from one language to another. When you navigate using Google Maps or some other application, it's not learning, but it's a smart AI system using search and planning algorithms, and so on, right? So deep learning these days is very popular. It's part of machine learning, and it deals with special models that are neural networks. So you can read it in the news about deep learning. It's very popular. It's really like pop music these days. Learning and AI. Well, we see from this is sort of a serious diagram, right? That machine learning is a subset of AI. But I have to adjust for the maybe too many coffees. So difference between machine learning and AI. If it's written in Python, it's machine learning. If it's written in PowerPoint, it's AI. So I have slides in PowerPoint. I will be talking about machine learning, so it's more theoretical. I will also show you some, not examples of code, but some libraries in Python that you can use. But you can also use other languages for artificial intelligence programming. Machine learning is actually popular among old people, like myself, for example, because the Python language is quite simple. If you know some other language and you come to Python, you say, wow, it's simple. It's not like C++ or Java. It's simple. Everybody can do it. And there's lots of libraries. I just use this library and I do machine learning all of a sudden, right? So that's why here is Python. So the title is Automated Machine Learning. So the goal that I will try to describe in detail is basically taking human out of learning applications. So that's a very prestigious goal, very strong goal. It's like creating an artificial mind that's the same as a human mind. So this will probably not happen completely, but in the way we will solve some smaller problems that are useful, right? Why we're talking about humans in learning application? If you have a machine learning problem, usually you get the data, and now it's up to you as a researcher, engineer, data scientist to choose the model. How do you choose the model? Well, if you're a statistician and you're doing statistics, you're an expert. you know about the models in statistics. So you probably choose some model from the field of statistics because you know how it behaves, right? If you're doing neural networks, so you think all problems can be solved by a neural network, just going deeper, you know, and create this big bada boom neural network. And maybe your traditional machine learning, and you like linear regression, or you like support vector machine, so you choose those. But basically, the idea is, well, maybe there's some automated system that can learn which model is good for which data. Or compose the model particular for the data. So that's the idea. I will get back to this, taking human out of learning application. That's sort of a rude comment, right? Like, you researchers, you're not needed, right? Sometimes we're reading that, you know, artificial intelligence will actually replace some professions from the market. But we usually think of like McDonald's, you know, people, that instead of a real people, there will be a touch screen and you order your Big Mac, right? Or El Corral to make it, you know. El Corral can have an order system and no people there. We don't want to replace data scientists. Well, we hope this will not happen ever, right? Because that's our job. I have to be slow. Okay. This is just the outline. So we will be talking about basic concepts, then the traditional machine learning models, then the deep neural network models, and then some resources where to go from here. So that's the idea. Basic concepts. This is not a tranquil image yet. So what's machine learning? Let's try to define it. It's sort of interesting. The field of artificial intelligence was coined in 1957. You know, the computers in 50s were big as this room, right? Were computing formulas only. And still people started to think about artificial intelligence. The idea was that the concepts we use when we deliberate, when we think of something and reason about things, how we decide what to do. Wow, that's a strong microphone. Can you hear me even? Well, now you can, right? This is okay too, or? I use microphone only when I have performance with my rock band, because we have a rock band. But we don't usually have that many people in the audience, so I'm really, really glad. So people in the 50s were starting to think that we can actually program the principles of human mind. And very recently, they were thinking that we can use learning algorithms to mimic the process of human mind. So there are several definitions what machine learning is. The one that's a computer program is said to learn from experience with respect to class of tasks and performance measure if its performance at task in time t as measured by the performance measure improves with experience. This is sort of a complicated way to say it learns something and then it performs better, right? Okay. This is gonna be that one. So this is the general scheme of machine learning, where you have your model, machine learning model, and you have some learning algorithm that basically optimizes some parameters of the model based on the data. The data are, for machine learning, are usually nice and clean. So we talk about features, the inputs to the model. And here is the real world, the dirty world. So the data engineers usually sit here, look at the dirty world of unreliable data, and try to create nice features of them, collect the data, clean the data, pre-process the data, and create a nice task of machine learning, right? Usually you have training data and testing data where you validate your model, but basically that's the idea. And then you take the model and use it for some other data, right? So that's the idea of machine learning. We have different types of machine learning. You probably heard of supervised learning and unsupervised learning and reinforcement learning. Do we all know what I'm talking about? Or that's very easily. Supervised learning is sometimes called, in Czech we actually have a translation that says learning with a teacher. So you have a teacher. Usually in the data you have the examples of input and desired output. And the desired output is like a teacher, right? So it gives you pregunta, and you say something as a model, and the teacher says no. You said 8, it should have been 9. Your error is 1. It's still okay, you know, could have been worse. So you can compute an error, and then the point of the learning algorithm is to adjust your perimeters, your brains, somehow, so the next time you answer 9. And this is called optimization. You formulate it as an optimization problem and you minimize the error, right? Usually it takes more iterations, right? You remember when you were trying to memorize a poem, for example, right? It's not like you first read it and you know it, right? So you create errors, but you're minimizing the error, learning better and better. And after several iterations, you know the poem, right? Yeah. So that's supervised learning. Unsupervised learning doesn't have the teacher. It has only the inputs. And so what is the task of unsupervised learning? Maybe you heard about clustering, for example. So the idea is you have lots of data and you should find representatives that represent the data very well, right? Like imagine you have data about people either having some disease or not, and only based on the observations, you should say, well, this group of people is having the disease, this group of people is not having the disease, right? So you find clusters, groups of data that have something in common. So that's unsupervised learning. And then reinforcement learning is the most complex one, and you can think of a robot trying to learn a robot something, right? The problem is that you have some kind of teacher, but the teacher is not with you all the time. The teacher is not telling you for every answer, is not telling you, you're right, you're wrong. Imagine a robot like a vacuum cleaner. If there's some dirt here and I'm a stupid vacuum cleaner, I just walk around, you know, and when I see some garbage, I take it. So in each step, I don't know if I'm doing right? If I move like this, is it good or bad? We don't know, right? But you can observe me and say, well, in 1 hour he collected, you know, 100 pieces of garbage, he's good, right? So the evaluation comes, but after a longer time. So that's why it's more complicated. I will mostly be talking about supervised learning in this talk, but it's just good to know that there are different kinds of learning as well. So, when we talk about the desired output of the model, and you will probably understand this more, with supervised learning we can talk about classification. That's like a medical diagnostics, for example. We can talk about regression, which you know from mathematics, right? Meaning that the output is real valued, so you sort of do like a regression of some function, basically. The clustering we mentioned, density estimation, statisticians know that, but we can also do some dimensionality reduction, and the reinforcement learning, the strategy of a vacuum cleaner in the environment. And as I've said at the beginning, the field of machine learning has lots of different approaches. So you can think of using some mathematical logic. There's inductive logic programming, where you use mathematical logic to create a machine learning model. the similar approach is you can define association rules. Rules are good because we understand them, right? Programmers understand them. If then is for programmers, we all understand. But even people understand it, right? Even kids, right? If you shout, I will not give you desayuno. Everybody understands that, even little kids, and they stop, right? We have methods that are very efficient based on statistics, the so-called Bayesian networks. We have decision trees, random forests. We have deep neural networks, and so on. So there are many different algorithms used in machine learning. And I will just tell you one theoretical thing that's sort of interesting, and that's also a good motivation. From the 90s, we know that when I was asking you at the beginning, which algorithm would you choose? Which machine learning model would you choose? We have a theorem that says that actually there is no machine learning algorithm that would be the best, considering all possible problems. So it's not like Lord of the Rings, right, where the ring ruled them all. We are in a situation that even if you have a favorite machine learning model, you have to know that for some data, this can perform very poorly. And then you should find the model that performs very well on this data, right? So it's called no free lunch theorem because it says, yeah, there's no best solution for every problem. You should always, for a given problem, try to find the best solution. But for the other problem, the solution might be different. Do we understand the no free lunch theorem? I mean, the no free lunch idea. Because, it applies for ladies more. If somebody invites you for lunch, says he's paying, it's probably not the whole agenda, right? Okay, so so this is no free lunch theorem. Another motivation is, this is an interesting example from 10 years ago. We all know Netflix, right? So Netflix wanted to develop a recommender system that would recommend you, oh, you watched Lord of the Rings, so maybe you should watch Hobbit, because it also has elves in it, and so on and so on. Right? So recommender system is important for the customers, because it makes you a loyal customer. And if it recommends well, it's like, wow, this novella was great, and it recommended that novella, and it was also full of corazones, and so they tried to improve a very simple linear model, and they actually offered $1 million to all programmers in the world, and it took them 3 years to improve by 10%. And the model is like this. It has 500 different models here, then somehow creates something linear from this. It has another 200 models. So we're talking about a model that's actually 1,000 methods, from linear regressions to statistical models, decision tree. 1,000 methods put together by dozens of human beings spent 3 years on this. Just improving your recommendation for the Lord of the Rings about 10%. That's just a waste of time, right? So there was an idea, well, a machine should do it, right? A machine should do it. Also, another motivation, if we're talking about deep neural networks, these models are really complex. This is quite an old model, and you see, these are modules having hundreds of numbers to optimize, and this is the complete structure of the neural net, right? So lots of parameters to choose. How do you create such a model? Again, most of the time it's created by humans experimenting, connecting the knowledge together, but it takes lots of time. For example, very recent example there is a model that is now used for natural language processing, like translations and so on. It's by Google. It's called GPT-3. Maybe you've heard about it. It's the most common model and the most powerful. It has billions of parameters. By training the model, creating the model, Google spent $4 million for electricity only. Just, $4 million US, electricity only. They said if it's like a one house where 1 or 2 families live in United States, where it's expensive, it's like 200 years of that house, So okay, we now have great model, but it has so many resources, consumed, and it's basically only Google that can afford this, right? It's difficult to develop another model like that. Yeah, we are all using it. If you've heard about DALL-E, that's an application where you just write down, I want a comics picture of Professor Juan Carlos Figueroa Garcia in traditional Ruana, teaching a group of parents. And this will produce an image, right? Haven't tested that one. So the automated machine learning should actually put machines instead of humans, right? So we're constructing machine learning programs such that without a human assistance, and hopefully with limited computational budgets, because we're not Google and we don't have $4 million to construct a good machine learning program. So that's the idea. And when I had before the simple example what a machine learning is, meaning we have a model, the features, and the algorithm, that's optimization. So now you can think of that from the feature to selecting the model, selecting the optimization procedure, and evaluating the model. This is all automated machine learning, right? We still need humans to be here and telling what is the problem definition, how to collect the data, and so on. But from the features to the evaluation, model selection, training, this is automated machine learning. Okay, it's how do you do it? How do you replace a human engineer by machine, right? Well, you should have a search space, because basically the machine will start searching, but searching for what, right? We should search for a good machine learning model. So we can have a library of methods, but we can create more complex methods, like ensembles of methods, connecting them with pre-processing. So sometimes this is called a workflow, the complete model, connecting more components. We can also search, the search space can be architecture of a deep neural network. Then we should have a search algorithm, a search strategy. So again, we're talking about optimization. We can use evolutionary algorithms. We can use a random search. We can use some local searches, gradient-based searches if we know that the search space is suitable, and so on. And we need a performance estimation, how to evaluate the model, right? Because basically you're trying to search through different models, and which model is good? Well, you should train it, right? But if the training of the model takes a lot of time, and you want to search through 1 million of models, you would spend 1 million of days. So this is not practical, right? Somebody comes with the data, and you say, well, I will deliver a perfect model, but in 10 years. They don't want it in 10 years, they want it over the weekend, right? So that was the motivation and basic concepts. This is pretty tranquil, I think. Now, in the next part, we will be talking about those classical machine learning models. So another term that's interesting is meta-learning. It's actually older than machine learning, and it says, well, that we should gather experience and use this experience to create better models. Sometimes it's really theoretical, but I will try to show you some examples that are not so theoretical. So the basic idea where you can use meta-learning is that you collect the performance of different models on different data, and you remember this. Because learning is expensive, so the result should be remembered. So you can have a database, a huge database of the results of different models on different data. And then your task is to recommend a model for new data, right? So what you should do is, well, I recommend a model based on previous results and look at the data and see if the data, the new data set, is similar to something I have already learned in the previous models, right? Do we understand this? It's like probably you don't know how to cook ahiako, but you have experience with some fish potato soup, and you say, well, this should be different. Well, it should be similar, so I start like this, and I don't know what's in ahiako. Put some avocado in it, and then it's ahiako. So how do you do it? Well, the first thing is to identify the soup you're familiar with, right? Oh, ahiako, I don't know, but I will zoom to my experience and see if there's something similar that I already cooked. Do we understand that? It's just called zooming because it sounds good, right? So you sort of zoom. I can cook different things, different carnes, but this is soup, so I'll zoom to soups, right? And find a similar soup. But imagine you're not the only cook, right? You have many cooks. So the idea, the second part is zoom into the soup that's similar and then see, well, how about Juan Carlos? How was Juan Carlos performing on the potato soup? Oh, nothing special. How about Juan Pablo? Oh yeah, Juan Pablo, you're the winner. So it's called ranking, and you select the algorithm Juan Pablo for creating the ahiako. Maybe it's not completely ahiako, but you start with there, right? So that's meta-learning. That's easy, right? You only need lots of cooks and a huge database of soups. And I will show you in the end that we have something like that for machine learning problems. I'll skip evolutionary computing because it's just one method, but I would just spend some time in the method that's called genetic programming that allows us to create programs by genetic-like procedure. And the idea is that you represent the programs as trees. You all program, right? You all are programmers. So you know how a program looks like, right? The compiler actually does not see the keywords. It translates it into some syntactic structure, and then it looks like a tree. So for example, an expression. So we all understand this type of expression, and this can be expressed like this tree, right? So what we're doing, we're dividing x by 11, right? That's this, so that's the division, right? Then we're subtracting this from 2.2, and so on and so on. That's easy, right? And we have a good automated procedure where you put those ingredients and it creates a tree that represents expressions. And you can learn it to represent the expression you want by supervised learning. So that's interesting, and I will show you another application of this. And this is it. When I was talking about more complex models, now you will see 3 or 4 examples of traditional auto machine learning And it's not a independent selection. I have selected the works I've been doing with my colleagues. So by now I was trying to be objective. Now this is more like subjective. But then we're being objective again in a while. So when I was saying how you compose the machine learning models, this is an example of the so-called workflow. And you have different acronyms here, and they are all machine learning models. So this is support vector machine for classification, for example. These are decision trees. You probably have heard of decision trees, a simple AI model, right? But these decision trees are together in the so-called boosting. That's one of the methods how you create ensembles of methods, how you put them together, right? These are three methods. This is multi-layer perceptron, a simple neural network. This is logistic regression, and this is quadratic roof. Oh, it's been 5 years, you know, so I don't remember. But these three are actually, again, put together by voting ensembles. So you see that the machine learning model is not just one model, but it's this structure of models. And you can actually represent this by the, oh no, this is too fast. You can represent this by the tree, and you can use the genetic programming procedure, but instead of the expressions like pluses and minuses, you actually have these operations and these methods. So that's one of the possibilities how to create the complex machine learning model. Another thing that is important is we were talking about the evaluation of the models. What is a performance of the model, right? Have you heard about multi-objective problems or Pareto optimality? I'll try to explain. It means you have more criteria. If you have one criteria, if you have only one criteria, maybe the error we were talking about, it's easy. You just want to minimize this criterion. But lots of problems in real life have more criteria, like 2, for example. So let me think. Public transportation, for example. Right? How you get from your home to the university. You can have different criteria. One criterion can be time. That's a good one, right? You don't want to spend a lot of time commuting to the university. Another criterion might be the price, right? And sometimes these two criteria are against each other, right? I mean, Transmillennium is cheap, but you sit there for an hour, right? A car is expensive, but hopefully faster, right? So for machine learning problems, we can also have different criteria. One of the obvious criterion is how the model is good in terms of its performance, minimizing the error. Another criterion might be the time again, right? Because we understand that if you train the model, the model performs better, but it can take 10 times more, right? So that's why we evaluate the models. So this is the time, and this is the error. So what you want is you minimize the error, and hopefully minimizing the time as well. But you can see that most of these guys, when you have good performance, it takes a lot of time, right? So this is called multi-objective optimization, where you want to somehow combine these two objectives, these two criteria, and usually what you're getting is this. These models are somehow optimal. In case that if you choose other model than this one or this one, like these, they are worse. But it's still up to you how to combine the criteria. Do I prefer the time? Do I prefer the performance, the precision of the model? It's like you choosing if you're using bus or car or a bike to commute, right? So it's important to consider those different criteria. with deep learning, one of the obvious criteria is how much does it cost to train it, right? We were discussing the $4 million model. So I'll skip this, and one last example that's actually sort of interesting. We did it with my colleague here. It's not published yet, so you're the first, besides me and Juan Carlos, who will hear about this. No, the reviewers at the conference, they already know. And the idea is how to use the experience. So there is a database of previous results, and it's called OpenML, Open Machine Learning. And everybody can submit the result. Like, we used this model on this data, and that's how it performed. Right? And it has nowadays, it has millions of examples like that, and you can actually use it the same when we were talking about the ahiako soup. Right? But this time, you imagine you don't actually call the cooks, the individual cooks, and let them perform the soup. You just read how well they performed, and they say, well, yeah, I better call Juan Pablo to Colombia to create the soup for me, because it's all in the database. So the performance estimation, you're not learning anything. You just see how they performed before. It's more complicated how to get the data right, but that's basically the idea. We now have huge databases of performance models indicators. Let it settle for 30 seconds. Because now we're getting deeper. Okay, enough. And now I will be talking about AutoML applied to neural network searches. It's called neural architecture search, and it's a bit different problem than we previously saw, but I will try to explain that the principles are pretty much the same. So, I said, we are using big architectures of neural networks. They usually have some layers or modules, and we would like to put them together so we create a big architecture that's also good. So far, all this has been done by humans who understand it. You have an expert on computer vision. The expert, she is using convolutional neural networks and doing some research how to create an optimal convolutional neural networks. So I will try to show you the architectures we can have and how we define the search space, what are the search strategies, and what is the performance estimation. And with the performance estimation, you will be surprised. I mean, search space is kind of boring. So yeah, in the area of deep neural networks, we have different architectures. The convolutional neural networks that are used for image processing. We also have autoencoders that are used a lot, for example, in natural language processing. How do you train a network that translates from Spanish to English? How do you train it? You know, that's actually interesting. I tell you what Google did, and everybody can do it, if you have $4 million. But the basic principle is simple. You have a network that's called autoencoder, meaning it learns identity. It learns just to repeat the input to the output. It sounds stupid, right? So you train the model, and if you say pero here, you expect pero at the output. The trick is that the network is big here in the input to have like the sentence, for example, the whole sentence. Then it goes like this. The middle part is small, and then it goes back again. It's symmetric to have the parallel as the output as well, right? So the network should actually learn some compression of the Spanish sentence into a space that's like between some kind of idealized for grammar, maybe, I don't know, some kind of Esperanto for neural networks. So you learn your Spanish autoencoder, you learn your English autoencoder, and then you cut them and glue the halves together. And then it accepts the parallel and it says dog, right? If you're lucky. So that's the idea. So we have many different architectures like that, and we actually what we want to search these architectures, right? The search spaces can be simple, just layers in a linear way, like this. We have input, the layers, and output, right? So for the encoder, these would be like big, and this in the middle would be small, and then big again, right? But we can have something like a tree or direct acyclic graphs of modules. It's not just a linear sequence, but it can go here, split the signal, and so on. So this is an example of those. You can have even more complex structures that represent current neural networks, where the structure of the modules is also trained, and you create a graph of a small networks, and then you stack them together in the linear way. I will not go into details. That's just the idea that we have one search space here and then one search space here to put them together. Right? It's like creating a team, right? So first you grow a good. What's the popular sport in Colombia? It's like in Czech. Okay, so imagine your idea is to. Oh, I understand suckers. Because Czech team is not very good. It has a famous history, and now it's sort of suckers. But congratulations to Colombians. So imagine you want to grow a good team of football players. So what you need is the team has different positions, right? So you have some kind of outer structure. You need a goalie and defenders and whatever, right? Different specialized players. And each of these players has to have special capabilities to be a good. Some of them have to run quickly. Some of them have to be good, kicking the ball, whatever, right? So that's like this. We have the team, and then we deal with each member of the team, right? So we're selecting good players, but for the position, for the special position in the team. It's not like universal player, right? So that's the idea of this. Nowadays, in neural networks, I said it's all handcrafted, mostly. So the good parts of the neural network, we know what they are. So if you deal with neural networks, you probably will hear about the so-called ResNet block, and it's just one block. So it means a good candidate for a special player, for a defender, or for an attacker, right? So we have ResNet blocks, DenseNet blocks, and so on. So now we don't start from scratch developing the blocks, but we are inspired what worked before. And we create the whole structure and connections and so on. Okay, so just something about how we search it. So it's always some kind of loop where the machine is doing the hard work. So we have the space of all possible players. We select some of the candidates. put together the team, maybe change it a bit somehow, the properties of the players. It's like training them or something. And then estimate the performance of the team, of the architecture. And we do it again and again and again. It takes, you know, hundreds, thousands of iterations. But basically it's this search that's, the principle is very simple. Sampling the search space, doing some perturbations, improving the players, estimating the performance of the whole team. And that's it. How do you estimate the performance of the whole team? Well, they should play lots of matches, right? But it takes time. So even if you don't create a national Colombian team, you don't want to start playing with all the teams all over the world. That's what you do on the World Championship, right? But to train them, you choose some, I don't know, friendly teams or something. Or you estimate, I'll show you that is really surprising. Oh, no, not yet. How do you estimate the performance? Well, you can use limited training. You don't let the players to play all 90 minutes. It's 90 minutes, right? Yeah. You just say, play for 2 minutes and we'll see, right? So that's a good strategy and we all understand it. The thing is, and it's called few-shot learning, so you don't learn the model for the whole time to see the performance. But recently they found out, so for the neural network, the training takes a lot of time. It's adjusting the parameters. But they found out that completely untrained network can actually tell you something about the performance. So, and this is pure statistics. What they did, they have like the untrained networks, meaning like, I don't know, small kids, you know, small future football players. And then they trained the networks, meaning let them grow and play many matches. And they saw who of them was like, I don't know, Pelé or Ronaldo, and so on. And they look at the young Ronaldo and says, well, he actually played better than most of the guys at the village playground. So they said, well, we don't need exact performance estimation, but this is enough. And for the architectures of neural networks, the untrained network has some information about how good this will be. It's not that exact information, but there is some correlation between those two things. So they tried it. And the idea is that if you don't train the network, just look at it, just try it as a young network, not trained. If it performs good, there is a high chance that this network, after the training, will perform good. So you don't train, you say, well, this is a pretty good one, we just use it. And this allows you to actually try million of architectures instead of 100. Right? So you sample much more architectures, sacrificing the precision, but then you select good candidate and train this candidate and spend the time on this candidate, because you don't want to waste the time on bad candidates. So this is called zero-shot learning, and it amazes everybody. Statisticians are, yeah, okay, that's correlated, should work. Right? There are some other examples. If you see how the training goes, we're minimizing the error, right? So what you usually see in the literature, it starts very bad, the error is high, and then it goes like this, and it goes lower, lower, lower. So we can actually look at this curve and say, well, I can extrapolate. If it goes like this, then maybe, you know, this will go like this, so I can stop here and say, I'll estimate it will go deep, right? If it goes like this, sort of lazy, then say, okay, in another hour, this will be here. Nothing special, right? So we just do a little learning curve extrapolation. It sounds like sophisticated, it's, you know, everybody can do it, just with a pencil. You can also take a look at some statistical properties of the model, especially for deep neural networks. If you compute some covariances of the layers and so on, so you can also estimate how good the model will be. So what I was trying to say, that even in the area of deep learning, where the models are complex, we can identify the building blocks, the layers or the modules. We can inspire by humans that were developing those building blocks. We can try, just stretching. So we're getting towards the preguntas. If you're interested, this is relatively new field, but we already have some books, two actually. One of them is called Automated Machine Learning, and it covers like 2/3 of what I've just said, but in detail. So this is one of the recommended books if you're interested. It's written as a textbook, so it's an overview. It's sort of I use it in a course for my master degree students. There's also a book called Meta Learning, the second edition. That's from last year, and so it's also one. And the best thing, these two books are for free. You don't have to steal them. They're open source. So when you're downloading them, you're doing a good thing. So they're for free. I was already mentioning the open machine learning. That's openml.org. That's the site where you can share your results, and you can use the previous results to recommend better models. So that's OpenML. There are lots of libraries, even for the traditional machine learning and auto machine learning with traditional models. So the traditional models are this, Teapot. In Python, I really recommend, if you use Python, I really recommend the scikit-learn library. Lots of models, easy to use. And then we have several, like 2 of these auto systems that work on top of a scikit-learn. So one of them is auto scikit-learn and another is called Teapot. We have some other libraries for languages like languages. Or Java, that's a real language for adult people. For neural networks, you have Keras based on TensorFlow, and nowadays PyTorch is used. So we have AutoKeras and AutoPyTorch for automatic machine learning based on those very popular libraries for deep learning. So you see that you can start actually, if you, for example, try scikit-learn in Python, then you can easily just download the auto scikit-learn and just try the automated machine learning there. Your first impression would be it takes forever, but it delivers better models. There are also some benchmarks if you want to do good research. The automl.org is a site that gathers papers and software libraries for the AutoML. Now we had the first AutoML conference this year. There are some fall schools organized in Germany. So if the students are interested, the fall school is actually a good opportunity for students to get in touch with the community and research possibilities. So, how to end? Well, at the beginning I said that the automated machine learning should take the human out of the learning application, right? That was the goal. Yes, as the ultimate goal, this is true, but what I like about those AutoML approaches is actually that they are making the machine learning more democratic, more accessible to people. Because you don't have to be an expert in the area of some of the models. You can, if you have some programming skills and you're an engineer, that you sort of understand what optimization is and so on, then you can basically use the library, right? And it recommends something. It doesn't have the bias we have, right? I've been doing neural networks for 20 years. I tend to like to apply neural networks to everything because I was doing it, right? This not, you know, this just takes all the methods, tests them, and you don't have to have deep knowledge how to use the models, how to tune the parameters. It will do it for you. Maybe not as good as a human expert in the area, but still it has some computational power and so on, and the algorithms are getting better and better. So I think that this is interesting to make the machine learning more accessible for people and for society in the long run. Non-experts can use this as a library and can obtain good models. The focus is that it's also available on standard computers, that you can in principle run it on a laptop, for example. You don't need a huge cluster of workstations, you don't need lots of computational time. Even though this might take some time, but the zero-shot learning, for example, makes things faster, right? And also not consuming vast amounts of energy. We are not willing to spend millions of dollars just creating another machine learning model. Right? And also we are not willing to spend 3 years of researchers to create an application. The researchers should focus on the algorithms, making this faster, right? And then you have a large community of data engineers, data scientists, people who are in the companies and who don't need to be PhD in machine learning, right? They can use the library on their computer. If the model looks promising, they can then use more power to fine-tune it. But that's the idea. So I think that the taking human out of learning application is true, but we should see it as an opportunity to present the models so all the society can use them. So thank you for your attention. That's it. Usually, if it's a concert and we have a big applause, we add another song. But I don't have any more songs, and it's time. If you have any questions, I'll be very glad to answer. ¿Preguntas? ¿Comentarios?
Dr. Roman, thank you very much. Very good, very nice conference. You said something about sports in machine learning, some samples. Do you have some samples about deep learning and sports? Maybe you know some applications? Thank you.
I just use the sports because you said it's... you can tell by my belly that I'm not an athlete, really. Well, what I actually know, that during the training phase, there are clever machine learning applications now used. I know from the cycling, because we were amazed. We remember Tour de France, for example, right? They go for 3 weeks in the mountains, on the bikes, 200 kilometers a day, and still the average speed is 50 kilometers per hour. I mean, try to go 50 kilometers per hour. It has to be downhill, and you will do it for 1 minute. And they go it, 8 hours a day in the mountains, And this was not like this 10 years ago. And so the experts are using optimized machine learning models that are actually learned on the physical properties of the racers, of the people. And they recommend the diets for them, so it's very specialized and personalized. And this allowed them, of course the bikes are a bit better, you know, and everything, but this special training program and nutrition and everything, timed, you know, minutes, like now eat the candy, now don't eat the candy for 14 days, and so on. Specialized programs using machine learning that adjusts to the data of particular sportsmen. So that's one of the, I'm glad I remember.
Thank you.
Yeah.
Gracias.
Thank you very much, Roman. We are so grateful with you coming here to do just such beautiful things. Thank you.
Back.
Thank you, Juan Carlos, for bringing it. You said we can compare Juan Carlos and Juan Pablo as cooks for some kind of soup. Well, that seems easy. But if you have some problem, just data, some classes, how can you know this kind of problem is comparable to this other kind of one to use for defense and use for goalkeepers?
That's actually a great question and a difficult one. I have one slide I skipped, so I'll just try to show you. And so what we want is to somehow define similarity on data sets, right? The similarity of data sets. And it's not easy. There are some things that are simple and sort of work, but let me see. Yeah, it's here. So for the data set, we can gather some metadata describing the data set, like how big the data set is, meaning how many items is in a data set, how many, so that's the rows, how many columns, how many features we have, type of the task, is it a classification, is it a regression, what the columns types are as well, is it just binary data or numbers, or do we have some categories and so on. So this is the simple things, right? Like quantitative, it does not tell you about the complexity of the data, right? Yeah. But then you can use some statistical properties. Even just computing simple statistics, for example, the columns and like covariances and things like that, it can tell you something, right? And so this is a question that's being researched. Still, we don't have definite answers, but you can go from these simple things up to describing the complexity, maybe the information, measures in the data. So it can tell you more how complex the data are.
Thank you, Ron, very much.
Difficult. Yeah, I was pretending everything's easy, right? Soups are similar, you can tell, right? But data is more complex. But still, even those like simple approaches work. No? Is it a green light?
Primero, yo lo paso por aquí.
Hi. I don't know if I understood well. The machine learning is on 10% today. O sea, tu capacidad de aprendizaje, o sea, no sé si entendí bien. La capacidad de aprendizaje de una máquina ahora es del 10%. ¿No?
She's asking about the example, Netflix example.
Yes. Yeah.
A lot of resources for only at 10%.
Yeah. Machine learning in general is mucho. The example was only this Netflix recommender system because it's a complex problem. Yeah. To recommend, simple problem is to recommend customers when they buying something. So if you go to OXO and you have some kind of card that records everything you buy, it can recommend you much better than movies. Movies are more difficult, right? But Netflix wants a good recommender system. So it was really difficult to improve by 10%, which seems nothing much, right? That was one particular example.
Another question. Is there a limit for the data that can you give a machine?
I understand the question. It really depends on time, right? For simple models, they can work with small data sets. The deep neural networks, they work with data sets that are gigabytes of data. The problem is that with gigabytes of data, it takes a lot of time. So for example, the model, the neural network, is good when you run 100 times through the data. If the data is small and one run takes 1 minute, for example, then the whole thing is 2 hours and that's fine. If the data is big, one run takes 1 hour and all of a sudden it's 1 week, right? So in theory, you can put more data into the model, but you should see how long does it take.
Thank you.
Sure. Pregunta here.
Hi, hello. My first question is about how necessary is to, I think, like separate the parts where the humans intervene in the, like, take part of the process, and what part is exclusive of the machine. I don't know.
Yeah, I understand. Yeah. I'll show the picture again and I'll tell you. So that's pregunta uno. We have more preguntas. So, model selection is, I try to show that it's one part that can be done automatically, easily. Algorithm selection and some kind of optimization of the parameters again, right? With the features, it's more complex. We have some methods how to select features, mostly based on statistics. So we can do some feature pre-processing based on statistics. We can do feature reduction by principal component analysis, for example, and so on. So we have good methods here, and that's why this pre-processing is also easily automated. We understand it, we just have to search the possibilities how to connect. This is really an intellectual capacity of an expert. You have to understand that you're talking about supervised learning problem. And you actually talk to the real people. Because if you do data science, you come to a company and they say, we have a problem, but they're not experts, right? So they don't even understand that you will need the data that you will use to train the model. They don't understand what supervised learning is. Do they have the examples of inputs and outputs as well, or not? Or only some of them? Are the data clean, or do they have some missing data? Lots of models is very sensitive. If you have some missing data, you cannot use the model, right? So here, it's still sort of, it's like an art.
Okay, and we can we take it as in terms of time? I mean, because maybe the reserve part for the machine is because the machine can operate faster than the human?
Yes, yeah. Definitely. The advantage of a machine is that it's much faster than human. On the other hand, if you're an expert, you're not searching the space blindly. You know where to go, because that's your experience, right? And I was trying to show that the search blindly will, even for the machine, will be too much. So you need to put some experience into the search. What is a good search? I have an example, if I may. Like how the computer plays chess, for example. This is one of the things where the computers are much better than humans. It's not just about the speed of a computer. Because if you see the possibilities how to move one move in a chess game and search all of them, this would still take forever, even for the fastest computer. Even go like 10 moves ahead. This would take forever. So you have to put some clever algorithm how to search the space, how to eliminate the bad ones and focus on the good ones and then go deeper in those, right? And this resembles the human thinking. And the best chess players, they don't search the whole space, right? They see there's one opportunity here, one opportunity there. So they focus and about the possibilities, and that's it, right?
Okay, and for that, can we say that maybe in a part you said that I think the data has to be like wide in the input and also in the output, but a little more condensed in the middle part. Maybe we can think that this wide and condensed part are related, that the condensed part is for the machine to interpret it, to understand it, and but the wider parts are for the human, the input and also the output.
Totally agree. With natural language, it's like that. We have found some squeezing of the information that's in the language. Yeah.
Gracias. I just have a question about the capacity of learning of some machines, and that brings me some old idea that maybe your meta learning and your meta systems can work with what we call the Bach-Michalovsky dimension. The capacity of the machine has to learn something to associate the problem with the machine. That's just what we are doing now. This is the size of my problem. This should be the size of my machine. It has something to do with that kind of dimensions and capacities.
It's difficult. It's difficult because I think it's a great direction. But so we, now we are in a phase where we are amazed that we can create big models that actually are applicable in lots of things. 10 years ago, we did not know how to create a classification of images. We cannot tell if there's a gatto or pero on a photograph. Now we know, right? We can even synthesize pictures. And of course the computers are faster, but not that fast. For deep neural network, the GPUs, the graphical processing units, help specialized hardware that accelerates this. But also smart algorithms, basically. So that's sort of similar to squeezing the information. We found out how to represent the image in a efficient way, basically. So I think, yeah, the speed and size of computers, it helps, but it's always hand in hand with creating smart algorithms. One more example, just a short one. The chess. So the chess is done since 1997. The game of Go, the Japanese game, sort of strategic game, was really unsuccessful for computers. And so we have to combine the chess algorithm with some machine learning that looks at the board with the figures, the white and black stones, and tells this is better for the black, this is better for the black. And this combination, finally, like 3 years ago, 4 years ago, led to a computer system that's better than humans. It was learning through the historical games, thousands of games, and combined it together with the search algorithm.
That you call experience.
Yeah, yeah. And the interesting thing, well, just one more thing, what else? So this was supervised learning of game of Go. Then they tried to not telling them the human games, to just let them play. Well, the algorithm was clever. It has all these components, but they say we're not telling you how humans were playing. We just let play and optimize.
They are too bad for this.
and it took 40 days of training on a huge cluster, and now the algorithm is better. So it learned without human assistance, and now it plays that we humans sometimes don't understand, but it beats us.
Thank you.
¿Alguna otra pregunta?
Okay, thanks. I was wondering if you can, or better if you think that talking in a long or short future, we can, as an engineer, work with AI, an AI, talking on cheap resources, because we all know that work with AI is very expensive. And also thinking about the useful or the works that we can make with the AI. It's not better take this feeding, when we talk about feed the machine to the meta learning, it's not better feed the machine with every custom that use this machine. It's a other way to can think about the meta learning and machine learning. I was wondering if this is correct or is very go of the idea. And if there is an opportunity of work with AI, meta learning, machine learning in the everyday workflow.
Yeah, I understand. Not yet, but there is a strong tendency. Even the deep neural network models are now trying to make them slimmer, smaller, so they can actually put them on your phone. Usually they're not there. If you have some assistant like Siri from Apple, it calls Apple, right? It records what you're saying, calls Apple, the Apple tells what you were actually saying, and then the Siri recommends something, right? So you have to be connected, because the neural network is too big to fit on the phone nowadays. But now we're trying to have lots of the architectures. I was talking about rest nets and dense nets. Now you have names of architectures like mobile net. They are specialized and they will be put in the phones. So on your mobile devices, probably you will not have the resources to train the model. But if you have trained the model, maybe on this one, then you can put it in the mobile and this can work there, right? So the to make the models smaller so they can be actually used in everyday devices is a big thing now, and lots of people are working on it. And the other thing about the meta learning and everyday experience, I think that's also a dream, to have some kind of system that you ask something, it will learn from it, but it's not there yet. I hope that in a few years we will have something like that. The best we really have is for data sciences, this OpenML side. If you do some experiments, take a look at what's already done, put your experiments there. But that's the best what we have.
¿Preguntas?
No, question.
Oh, you do?
In all these models, data is treated like as some kind of deterministic data, coming as examples, and blah blah blah. And the usual way to represent the uncertainties by probabilities or statistical learning and so on. But there are many other kind of uncertainty sources. So how do you think this machine learning is trying to handle and manage other kind of
it's also a good question, and I have to say that it's sort of a painful thing, because we're in general, I would say that the models we understand, like rules, for example, we understand, but they are good for very simple problems. The models that are successful now are those neural networks or combination of models. And basically we don't understand how they work. They work, but we don't understand. So we can say something about the stability because we can test the statistical properties, and we understand that the learning sort of regularizes things, chooses towards averages or means if it doesn't know, but that's as much as we can say, right? So unfortunately, that's sort of an absurd situation. The models we understand are not good enough in learning. The models that are good enough in learning, 10 millions of real numbers. We don't understand what that means. And that actually can create a danger, because we know that even those classifiers, like distinguishing cats from dogs, you can actually feed them the data that for you it looks like a cat, but the model tells it's a dog. So now we have the so-called adversarial attacks on those machine learning models. And I suspect that, in a few years we will have hackers hacking the artificial intelligence, not just your Unix password or something, right? Yeah. So I'm sorry I disappointed you, but ask in 10 years.
¿Tenemos preguntas? Ah, sí.
Última.
Hi, first of all, thank you so much for the conference. I have two questions. First, I would like to know your opinion about new websites that allow people to create code using natural language. And second, for example, if I want to create a credit model by a company, should I use a database local or use big data?
Yeah, I think that using natural language to create a program is one of the showcases of the technology. It's good to show that it works somehow. It's the same as describing the image with the DALL-E model, and it produces the image. This will never replace an artist, and those systems will, well, I'm not sure if ever, but definitely not in the next generation, they will not replace a programmer. Definitely not. Being a good programmer is much more than the neural network can learn. But it's a nice showcase example that, for example, for kids in schools, this can help, right? Because for them, the syntax of the programming and all those keywords in English and different symbols, it's difficult at the beginning. If they have something like that, hey computer, move my mouse robot, that's fine. I like it. That it will not replace the program in the near future. And the second thing, I think that these days, lots of companies are trying to sell you the cloud time and tools for your experiments, even with machine learning, right? So if you know what you're doing, and you can use your scikit-learn, for example, to try it on your machine, I think it's the best start. And if you see that you need more resources, then there's lots of services that are actually not that expensive, that you can rent a machine that has all the libraries and everything. So basically moving from your laptop to Amazon or Google server is very easy. But I recommend start locally and use those resources if you need them. Muchas gracias. You were a great audience. Thank you. Thank you very much.
Estamos desde la nueva alquimia. Funciona, pero no sabemos cómo. Necesitamos entonces de una nueva ciencia.